Okay, if everyone can take their seats. For the last people coming in, there's a few seats down here. We're going to get started for the evening. Welcome to the 2025 Stibbs Lecture. I'm Professor Tara Murphy, Head of the School of Physics, and it's great to see all of you here for this really special evening. Firstly, I'd like to acknowledge that we gather on Gadigal country, country where discovery and learning have happened for millennia. Country that's been home to knowledge sharing from generation to generation. Country that's never been ceded. As we meet today, we acknowledge and pay respects to the Gadi people and to the knowledge and learning that are embedded deeply and forever in Aboriginal and Torres Strait Islander custodian of country. As we mark 175 years of the university's history, we acknowledge that this place has been a place of learning and knowledge exchange for over 60,000 years, and that this wisdom has been passed down through many generations. Tonight we're here for the Stibbs Lecture. Professor Walter Stibbs was a distinguished international researcher, best known for his contributions to stellar astrophysics, for his global scientific leadership, and for his outstanding mentoring of students and young researchers. Professor Stibbs was a graduate of the School of Physics at the University of Sydney, receiving the University Medal in 1942. He went on to a long career in Australia and the UK and held many senior positions, including in the Royal Astronomical Society and the International Astronomical Union. The Professor Walter Stibbs Lectureship commemorates his achievements through an annual lecture by a distinguished astronomer of international standing. And this evening, I'd like to offer a warm welcome to Helen Stibbs, daughter of Professor Walter Stibbs. I'm so glad that you could join us. I would now like to introduce our speaker for the 2025 Stibbs Lecture, Dame Jocelyn Burnell. In 1967, as a graduate student in radio astronomy at Cambridge, Dame Jocelyn made one of the greatest scientific discoveries of the 20th century. She became the first person to detect pulsars, rapidly rotating neutron stars that emit powerful beams of radiation. This serendipitous discovery opened up a brand new field of astrophysics and led to her supervisor being awarded a Nobel Prize. Since then, Dame Jocelyn has forged a career defined by both scientific brilliance and pioneering leadership. She became the first woman to serve as president of the Institute of Physics and the Royal Society of Edinburgh, and has led major international projects, including as project manager during the construction of the James Clerk Maxwell Telescope in Hawaii. A tireless advocate for diversity in science, she was instrumental in establishing the Athena Swan Initiative, which continues to advance equity and inclusion across universities worldwide. Her achievements have been recognised with many of the world's highest honours. She has received the Royal Astronomical Society's Gold Medal and the Royal Society's Copley Medal, and in 2018 was awarded the Special Breakthrough Prize in Fundamental Physics, one of the most prestigious awards in science. In a characteristically generous gesture, she donated the entire $4.3 million to fund scholarships for postgraduate students from underrepresented areas in science, with a particular focus on women. She has been appointed Dame Commander of the Order of the British Empire, and this year was made a Companion of Honour for her extraordinary contributions to astronomy and education. Earlier this week, I was privileged to be present when Dame Jocelyn was presented with an Honorary Doctor of Science from the University of Sydney in recognition of her outstanding contribution to the field of astrophysics, her passionate advocacy of underrepresented students in STEM, and as an inspirational role model for women in science. As a woman in science myself and a radio astronomer, it is with great pleasure that I welcome Dame Jocelyn Burnell to the stage to present her talk for this evening, Reflections on the Discovery of Pulsars. Dame Jocelyn.
Thank you very much. Is my microphone working? No. It might now. Switching things on is quite a good idea. Thank you very much for that generous welcome, and thank you to all of you for turning out this evening. What I want to do is tell you a story, a true story, at least true as perceived by me, and it goes back, quite a few decades. You'll probably pick up the details as I go on. So I'll say a little bit about radio astronomy, a little bit about quasars, and then, having given you that background, talk about being in Cambridge and the discovery of pulsars, and a bit about what are pulsars, all in under an hour, I hope. So this is what we call the electromagnetic spectrum, and you can see a little rainbow in the middle. That's the fraction of the electromagnetic spectrum that our eyes can respond to. Our eyes don't see anything to the left or to the right of that little rainbow, but there are a lot of other similar radiations, like light, that's in that rainbow. I'm going to be talking about radio astronomy, and that's down to the left. Wrong button. I think you probably can't see this terribly well, but the radio is at the left-hand end of this spectrum. So go out the red end of a rainbow and keep going, and you come to the radio region of the spectrum. This is a radio telescope, wonderful picture. It's the very big telescope in Britain called the Lovell Telescope at Jodrell Bank. It's about 250 foot across, and it's a very big structure. It tilts, and it also turns. It's on a circular track. So that combination of turning and tilting means it can see almost every bit of the sky. Although I have to say it avoids looking towards Manchester, because the city of Manchester produces quite a lot of spurious radio signals. And they're a lot stronger than many of the cosmic signals. So radio astronomy developed following the Second World War. A number of people who'd worked in radar transferred to working in radio, which is just like the receiving bit of radar, so to speak. And radio astronomy really began booming. Very, very quickly, they discovered that there were all sorts of objects up in the sky, in the cosmos, that gave radio signals. So they were immediately presented with a wealth of material. And there was a particular set that were fairly strong, but when they got good positions for these radio emissions and said to the optical astronomers, "What is there?" The optical astronomers would say, "Well, looks a bit like a star. Slightly funny kind of star, but a star." And so these things became known as quasi-stellar radio sources, or quasars for short. It turns out that they're very, very distant, and so they must be intrinsically very, very strong, since they seem quite bright to us. Right, my story. I started life in the north of Ireland, number one. Born, brought up there, went to school there till about the age 12 or 13, and then got sent away to boarding school in the north of England in York at position number 2. Northern Ireland has had difficult politics for eons, difficult relationships between Protestant and Catholic communities, quite a lot of violence. Bit better now, but still underlying it all, there's some of those issues still with us. And everything in Northern Ireland is divided into Protestant and Catholic, even the schooling system. So this division really means that both sides are a bit underfunded, but putting them together is dynamite. So that's where we are. So I got sent away to boarding school in England at age 13 for most of my secondary education, and that's number 2. I then went to the University of Glasgow, which is number 3, to do a physics degree, bachelor's degree in physics. And you see those places are all towards the north of the country. I then, very much to my surprise, got a place in Cambridge at number 4 to do a higher degree, a research degree, a PhD. And it's a good deal further south. So I turn up in Cambridge with the kind of accent I've still got, and people kind of look at you a bit suspiciously. I was also aware the streets, particularly in the centre of Cambridge where there's not much traffic, lots of young men walking around, university students, walking around debating in very loud voices about what Pliny had said and what Pliny had not said. And I've come from this very down-to-earth university in Glasgow and think, oh my God, this is a funny place. They're all terribly bright. Well, they weren't, they were just showing off, but they took me in. They're very bright. I'm not that clever. They've made a mistake admitting me, and they're going to discover their mistake and throw me out. In case any of the students here encounter that feeling, and you may do, because as you move from one kind of education to another, it's quite scary. But if you ever feel, oh, they've made a mistake, I'm not bright enough, here's what you do. You do not run away. You say to yourself, yeah, maybe they're going to throw me out, but until they throw me out, I will work my very hardest, so that when they throw me out, I won't have a guilty conscience. I'll know I've done my best, and I just wasn't bright enough for that place. So that was the approach I took when faced with these apparently incredibly bright people in Cambridge. And it works, so I do recommend that to you as a policy. The alternative is to say, I'd better leave before they throw me out. But that's running away. You don't run away. That's not allowed. That's not an option. You hang in there and you do your very, very best. Discomfort grew a couple of days later, starting work in the Cavendish laboratory. The first thing that happens is that the new graduate students are presented with a set of tools. These are my actual tools. I still have them. These are not microelectronics tools. These are full-size, heavy-duty wire working tools, because that's what I'm going to be doing. So I spend the first 2 years being part of a team building a radio telescope. There was a lot of heavy work. There was a lot of what we called sledgehammering. What phrase do you use? You know? Same thing, sledgehammering. There was a lot of sledgehammering of posts into the ground. I was spared most of that, but I did do enough that I, when playing field hockey, could hit the hockey ball from one end of the pitch to the other. You become quite strong after just a little bit of this hammering. My hockey team never learnt. I was playing full back, and the forwards would watch the ball go by and say, oh, Jocelyn, how are we meant to get that? Start running. Anyway, so, yep. Surprisingly, I don't have back problems. I thought, you know, this may end up as something like that, but actually it's worked out okay. So I'm part of a team that's building a very large radio telescope. It occupies the same area as 57 tennis courts. It's huge. In British currency, it's about 4.5 acres. So it's very, very large. It was relatively cheap because the labour wasn't added into the costs. It was a lot of wire, but there were about 6 of us that spent 2 years building that equipment. This particular slide is getting well on through the process. My responsibility was all the cables and the plugs and the sockets that went on the ends of cables. And in this particular slide, we are checking that, yeah, it's just not bright enough. Okay, my colleague Don Rolfe, is standing at one end of a bunch of cables that stretch all the way to the distant little red and white hut. I have spent the winter, the Cambridge winter, in these two little red and white huts, putting plugs and sockets on this special low-loss cable that you cannot coil up and take indoors. You have to work with them stretched out. It was not warm, I can tell you. The connections were all good, which was really great. There were about half a dozen of us that worked for 2 years building the radio telescope. It involved a lot of hammering, and I was spared most of it, but I did do a bit. But my main responsibility were all the cables and their plugs and sockets. This is the finished article. This is actually a radio telescope. A radio telescope that works at quite long wavelengths, so you don't need solid reflectors. Strands of wire will do, for instance. And it's huge. It occupies an area of 4 acres. That's many, many, many hockey pitches, I can tell you. And this is only part of it. Lots of wooden posts. Pointer, I think, is not bright enough, but you can see lots of wooden posts. That's because there's a lot of bare wire. And if wet grass touches bare wire, the electrical signal goes down to earth. So you've got to keep it up above the height that grass will grow to, for a start. There's a lot of copper. You can perhaps see a number of the bluey-green loops of copper coming down from the actual antennae into the feed wires, collecting together the signal from all these antennae. There were almost 2,050 antennae. It was very, very big, and tons of copper went into this. Ultimately, when the telescope ceased use, the tons of copper disappeared one night. Right, so over 2,000 antennae, 81.5 megahertz. That's a wavelength of about 12 feet for those who still work in these old units, so it's quite long wavelength. Over 1,000 wooden posts, almost 200 kilometers of wire and cable. And it's actually electrically in 2 halves. So we can use it as what's called an interferometer, the 2 halves being separate, each detecting themselves, the radio signals. Transistors were just coming in, but they weren't considered reliable enough. Whoa, noisy, whoa, unreliable. We use vacuum tubes, or valves in Britain. So, yeah. One great advantage of those old vacuum tubes is if the thing stopped working, what you simply had to do was to thump it. That caused all these valves, vacuum tubes, to get reseated in their sockets, and it usually worked. With transistors, that technique doesn't normally work. Now, the science behind all this. We're interested in quasars, quasi-stellar radio sources, which were fairly recently discovered and were intriguing and quite a puzzle. They're really very, very strong radio sources, and you'd normally think the strong radio sources are the nearby ones. But actually, it turned out they were extreme distances, a long, long way away from us. So they should have been faint, but they weren't. So they must be intrinsically incredibly bright if they look bright and are at those fantastic distances. So there was a lot of questions about what exactly they are. We now know that there's a massive black hole in their centers, and that the material is being pulled into the black holes all the time. They're gathering material and growing. And they are very, very distant. I mean, not just beyond our galaxy, but miles, zillions of miles beyond our galaxy. The technique for detecting them was quite a neat one, but it's a little hard to explain, so apologies if I lose you on this bit. So the diagram, upper half of the diagram on the right-hand side, there's an object called a quasar, which is very far away, way, way, way up there, millions of light years away. And there's a radio telescope on the Earth. And to see the quasar, you've got to look through the space between the Sun and the planets, the space around the Earth. And that space is not empty, because the Sun is sending out hot plasma all the time, where it's sufficiently hot that the electrons and the protons have separated. It's highly ionized. And it's not smooth, it's a bit blobby. And so I've illustrated that with, you can see 3 blobs across the middle. That represents the solar wind and the irregularities in the solar wind. And a radio wave coming down and meeting something blobby like that gets spread in several well-defined directions. Those of you who've done any physics may have come across a diffraction grating. This is a bit like a diffraction grating, but it's not for light waves, it's for radio waves. And if you've got a very compact object like a quasar, and the solar wind is blowing sideways, the kind of signal you pick up is jittery, because sometimes you're picking up the signal through a gap between the blobs, and sometimes you're picking up the signal that has gone through the blob, and it ends up with a bit messy. If you have a very extended object, not a compact one, then some of the rays will come through a blob, some of the rays will come through a gap in the blobs, and there's really very little change in the brightness of the source. But with a very compact source, it's going to show this scintillation or fluctuation as the radio waves come through our blobby solar wind. Right. Not a perfect analogy, but quite a useful one, is the pattern you get on the bottom of a swimming pool when the light shines through the waves on the surface of the swimming pool. There are some spots where the light concentrates, and there are some spots where there's very, very little light. Can you imagine lying on the bottom of a swimming pool, looking up, and there's a little gentle wind, so that pattern blows past you? And sometimes you see some of these bright streaks, and sometimes you're looking at the space between the streaks. And the signal you get bounces up and down. That's the nearest analogy I have to this scintillation of the quasars. The important message is, if you've got a compact object like a quasar, and you view it through the solar wind, its brightness is going to appear to change quite rapidly. If it's a very broad object, then some bits are being faint, some bits are being bright, and the whole thing doesn't change very much as the pattern blows past. Right, quasars. We're way back in the early 1960s. And this gentleman is a Dutchman, temporarily for Schmidt, Martin Schmidt, although he's working in the USA, as were many people, I have to admit. And the radio astronomers, this is very early days of radio astronomy, but the radio astronomers have identified some very bright objects in the radio sky. And they say to their optical colleagues, "What's there?" And the optical colleague says, "Yeah, bit peculiar. Looks a bit like a star, but not a proper star." And so they became known as quasi-stellar objects, or quasars. It turns out they're not stars. They're more like whole galaxies, but quite compact, and they're at a great distance. So they're known as quasars or quasi-stellar radio sources. So the radio astronomers are turning up quite a lot of these quasi-stellar radio sources, or quasars. And the onus is now on the optical astronomers to tell everybody what the heck those radio astronomers are seeing. And Martin Schmidt and a colleague each of them have got a spectrum, an optical spectrum of a quasar. Martin's is 3C273. That's the name of a rather famous radio source. 3C is third Cambridge catalogue, and it's number 273 in the catalogue. And we now know that these things are very, very distant, but it wasn't known then. And Martin is puzzling over the optical spectrum of this quasi-stellar object. And he says it looks awfully like a hydrogen spectrum, and that would be perfectly normal. Hydrogen is the most common element in the universe. Looks awfully like a hydrogen spectrum, but it's way shifted to the red end of the spectrum, which means the object is moving away from us at huge speed, which means it's very, very distant. But it's very, very bright and very, very distant. How does all this work? But he thinks, it does look like a hydrogen spectrum shifted to the red end of the spectrum. And he goes along the corridor to his colleague and says, what do you think? I don't have a slide about his colleague. His colleague has another spectrum, a spectrum of another quasar, an optical spectrum. And Harry says, hey, do you think it could be hydrogen with a large redshift? Oh, you know it could, but it is a huge redshift. And Harry goes home that evening and says to his wife, something terrible happened at the office today. Because a very large redshift means a huge, huge distance. And it also means you're seeing it earlier in time. It's very bright, but it's at a huge distance. Those two don't tally. And yet they have to tally. So he's really, really puzzled and a bit anxious. So something terrible happened at the office today. So radio astronomers continued observing and found some more of these things that turned out to be equally quasi-stellar with huge distances, huge redshifts. And at the point that I turn up in Cambridge to start a PhD, they know of about 20 of these objects. And the optical astronomers will say, yeah, it looks a bit like sort of a distant galaxy, but it's not quite a normal galaxy. And it's belting out radio waves, whatever this thing is, because it's one of the strongest things in the radio sky. So considerable puzzle. And my particular project is to find more of these objects, more of these quasars. And they're very compact objects. And if you view a compact object from Earth, through the Earth's atmosphere, through the ionosphere, which is always sort of bubbling around, the intensity, the amount of radio signal you get changes because of the intervening medium being a bit bubbly. And it'll only change if the object is very compact. So the idea was that we could pick quasars out because they were strong, but they're a bit up and down in brightness, they're a bit bubbly. And the idea was to build a very big radio telescope and to operate it with what we call a short exposure time, short integration time, so that we could see the bubbliness of the brightness. Because there are other things in the universe that emit radio waves, and we really wanted to discard those. We're only interested in these very compact objects. So I arrived at the point that my supervisor, thesis advisor, Tony Hewish, had got funding to build a very big radio telescope to look for more quasars using the fact that their brightness changed. And I spent the first 2 years of my PhD on a construction project. There may be people here thinking of doing PhDs after their degrees. You don't necessarily end up doing the kind of thing I did, but just some of you might, so be prepared for anything if you go for a PhD. It was a very successful project. I got the number of known quasars up from about 20 to close to 200. So that gave us a good sample. But it was quite hard work. Having done 2 years of quite heavy manual labor, I could literally swing one of these sledgehammers. I then had my third and final year of funding for operating the telescope, analysing the data, writing a thesis, doing a PhD viva, all in 12 months. University of Cambridge had a computer at that point, but it was a very small, primitive computer with less memory than your laptop. And very few people could have time on it because it was so small. And we didn't. I didn't. My data came out on long, long rolls of chart paper and were analysed by hand. And this is an example of the analysis going on. 30 meters of the chart paper produced every day. And I ran the project for 6 months. So I had over 5 kilometers of that chart paper. And I've scanned every centimeter of those 5 kilometers, I can assure you. But a lot of life in my final year. The PhD program in Britain is just 3 years. So 2 years building a radio telescope, 1 year running it, analysing the data and writing a thesis. Quite compact. 120 meters for one sky scan, and then start again, scan, start again, scan. And as I say, I ended up with over 5 kilometers of paper. This is a tiny piece of my chart recording. I got used to identifying the twinkling quasars, the scintillation of quasars. Found a lot of quasars, so it was highly successful. But I'm still scared. This is Cambridge. I'm not bright enough for this place. They're going to discover I'm not bright enough. They're going to throw me out. I'm working very, very hard, crazily hard, it has to be said. And I just about managed to keep up with the flow of the chart paper coming in and found lots and lots of quasars. But in amongst it all, found a little signal that I couldn't make sense of. And this slide shows the first example of it. Now, what you're looking at is a signal that is high pass filtered. I've allowed the high frequency signals through and cut out the slow drooly things, because I'm not interested in the slow drooly things. I'm interested in things that show this rapid scintillation. Those are the quasars. So the signal you see up there, the slow drooly stuff has been filtered out, and what I'm looking for are examples. This doesn't really show. Examples of fluctuations. This particular piece of chart paper shows 2 examples of fluctuations, neither of them a quasar. There's some radio interference in the center of the slide, and at the left-hand end is a little signal that I couldn't make sense of. Remember, I'm going to get thrown out. I'm working my very hardest so that when they throw me out, I won't have a guilty conscience. And I take note of that funny little signal on the left-hand side. Let you go back. I showed it to my thesis advisor and said, "What do you think this is?" And he said, "You stupid fool." That's the way interactions with my thesis advisor usually began. "You stupid fool. it's all jammed into about 4 millimeters, and we can't see what's going on. We need an enlargement. And with chart technology, enlargement is easy. You run the paper faster under the pen, and it all gets spread out. Neat. Except you can't leave it running at that speed, or it'll get through the whole roll of paper in 20 minutes. And guess who lives at the observatory putting a fresh roll of paper in every 20 minutes? Next best idea, grad student goes out to the observatory shortly before the telescope would be looking at that bit of sky, switches to the high speed, and see what happens. And this is what happened. The top line is the signal that came in, and the bottom line is man-made 1 second time marks. The 1 second time marks are beautifully regular. The signal that comes in is actually not bad. There are distinctly pulses that are equally spaced. Okay, they come in different strengths, some are missing, but when they're there, they're pulsing nicely, and even after a gap when they disappear, they reappear on cue. So it's a weak signal, you can't always see it, but the thing giving the signal is pulsing steadily, whether or not you can see it. And it's pulsing at a period of about 1 1/3 seconds. So I asked my supervisor what he thought the heck that was, and he thought I'd wired something up wrong. So he comes out to the observatory next day at the right time, watches me set up, and sees it with its own eyes. And we can see on the next day that it's pulsing at the same rate as the previous day. Now, Tony has labelled this bit of chart, that's Tony's writing, LGM1. LGM stands for Little Green Men. I did not seriously think that we had detected little green men. It was a possibility, but given that I fairly quickly found a second, a third, and a fourth, the little green men hypothesis gets a bit shaky. There might be one lot of little green men signalling to us. There are unlikely to be 4, all using the same frequency and the same technique. But they became known as LGM 1, 2, 3, and 4, just for the hell of it. So that's duly labelled in Tony's handwriting, LGM 1. And the bottom line are these time pips that were broadcast, which were very useful. And although the strength of the signal varies, and sometimes it disappears completely, when it's there, it's exactly on cue, and it's pulsing at a period of about 1 1/3 seconds. So what the heck is this? It's probably some kind of terrestrial interference. Something on Earth is generating radio waves. You know, it's maybe a military radar station or something that's overspilling and our telescope's picking it up. We spent a lot of time, we spent a lot of time trying to work out what the heck it was. It kept its place amongst the stars. You know that in wintertime you see different constellations in the night sky compared with the summertime. That's because the sky, the stars, don't go round in 24 hours. They go round 23 hours, 56 minutes. And so the constellations we see in the night sky change during the year. Whatever the source of this thing was, it was coming back 23 hours, 56 minutes later, and then going ding, 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 the way it had done the day before. And 23 hours, 56 minutes after that, our telescope would pick it up again, and it's going ding, 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 the way it did yesterday and the day before. I had to make a lot of observations to ascertain that. Now, because it's keeping accurate time, it's not getting tired, it's big, and it's got large energy reserves. But because it's beating very, very fast, it must be small. So it's big and it's small. Yeah. We can be a little bit more specific. It's small in dimension, width, but it's big, maybe in mass or energy. Still a bit hard to reconcile those two, but at least we've clarified it a bit. There's a technique radio astronomers can use to get the distance of an object. It's called a dispersion technique. When radio waves come through space or anywhere where there are free electrons, the radio waves don't all travel at the same speed. I know we're taught that light travels, see the speed of light, radio waves travel at the same speed. That is in vacuum. The space surrounding Earth, immediate space surrounding Earth, is not a vacuum. There's ionosphere as well as atmosphere. There are charged particles, and those will affect the speed at which light travels and the speed at which radio waves travel. And we could use another version of that to get a distance to the sources. Space itself is not totally empty. There are free electrons, and a radio wave coming through, quotes, empty space actually gets dispersed with the higher frequencies going faster than the lower frequency waves. And using this dispersion, we got an estimate for the distance of this object of about 200 light years. That puts it way beyond Pluto, way beyond the Sun and the planets, but still within our galaxy. Yippee! There's only 100,000 million stars in the galaxy, so it's one of 100,000 million, maybe. But at least we've got an estimate of the distance. Now, I had used this nickname, Little Green Men, and we had to check that out somehow, because if we literally are detecting little green men, we probably have to tell the military, or the Home Secretary, or who do you tell? We don't know, but we'd have to tell somebody. So we did need to check that one out. If it is little green men, they probably live on a planet which goes round their sun. And as the planet comes towards us, the pulses pile up on each other. The space between them is shorter. And as their planet moves away from us, the space between the pulses increases. So, Jocelyn, keep making these recordings every day, please. And we'll look and see if we see any sign of the period changing as the little green men go round their sun. So Jocelyn and Julie did that along with everything else. We could find no evidence of any change in the period, other than a sort of aging as the whole system got a little bit tired, but no sense of little green men orbiting their sun. And then, thank goodness, I found a second one in a different part of the sky, and a third one in yet another bit of the sky, and a fourth one in yet another bit. The first three were all pulsing, each had their unique period, but they were around about 1 1/4 or 1 1/3 seconds between the pulses. The fourth one was much faster. It had 4 pulses per second, so going ding, 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 ding. And it's a bit hard to envisage what massive cosmic object be going ding, 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 ding. But it was, clearly. So that was going to stretch the theories, undoubtedly. We wrote up the first one and published it in a separate paper, and then the other 3 came in a second paper a few weeks later, sent it to what I think is fair to claim as the leading English language journal, which is called Nature. It's nothing to do with naturists, so don't get excited. And following the publication, the press took an interest. And this, for me, was a very difficult time. The press would talk to my thesis advisor about what they'd found, what we'd found, what the significance of it was. And then they turned to me for what they called the human interest. What were my bust, waist, and hip measurements? How many boyfriends did I have? Would I describe my eyes as blue or azure or green or what? really intrusive questions, because young women at that stage were simply sex objects for the newspapers. And never mind that I'd made a major astrophysical discovery, what was really important was how many boyfriends did I have. And I found that very, very difficult, and my male colleagues did nothing to distract the journalists or in any way diminish the inquisition. I hope young women today wouldn't be subject to quite the same thing, but certainly women of my generation, I think, will know what I'm talking about. And if anybody of either gender in the audience hears any of that going on, please intervene and tell the journalist to get lost or something even stronger. But one of the journalists was quite interesting. He's from a leading British newspaper, a bit conservative, well, very conservative as a newspaper, but they did have good science coverage. His name was Anthony Michaelis, and he was one of many journalists who interviewed Tony and I. And the interviews themselves were interesting. Tony would be asked all the technical questions, and then I'd be asked for my bust, waist and hip measurements, and please could I undo some buttons for the photographs and all that. This particular journalist asked us what were we going to call these things. And we'd given some thought to that. It was something like pulsating radio sources or pulsed radio sources. We moved away from pulsed radio sources because it might imply some aliens making the pulses. And we didn't want to go down that route. So we said pulsating radio sources. And Anthony Michaelis said, no, rubbish, that's far too long. What about pulsars? We already had quasars, so pulsars was a good idea. And pulsars, they became known, thanks to Anthony Michaelis of the Daily Telegraph. So what are these pulsars? We now know of very many, even if the computer won't know me. There we go. Right. So we have a very compact star with a very large magnetic field, and the magnetic field forms a beam of radio waves. The magnetic axis is offset from the spin axis, and so as the star spins, this beam cones around the sky. And if the Earth happens to be where the beam falls, we see a pulse, 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 and so on. It's a bit like a lighthouse. We now know that these objects are very small. They're about 10 miles across. And for something astronomical, that is very, very small. They're also very dense because they weigh more than our sun weighs, about 1.5 times the mass of the sun. But it's all jammed in a ball with a 10-kilometer radius, about 10 miles across. Fantastically dense objects with a lot of very interesting physics. There's a branch of physics called condensed matter physics. That's tiddlywinks compared to what these are in terms of being condensed. Their structure and their insides are really very extreme and very, very interesting. Good, that's moved on. So we found them in the radio wavelengths, and that's still the prime search area, search frequency band. There's only one that shows anything in the visible. They are primarily radio objects. Some produce X-rays and gamma rays as well. And there's now about 3,000 of them known. About 20 of them have some light, some visible that you might see, but by and large they are not optical objects. There's about 100 that you can see in X-rays and about 200 that you can see in gamma rays. So rather more in gamma rays than X-rays, which is interesting. Of the 3,000, about 10% are twinned with another star, Many stars up in the sky are twinned. Of these, it's only about 10%, but you can see by seeing the way the period changes as it orbits an invisible companion that it is orbiting an invisible companion. There's one case where two pulsars orbit each other. And there's a triple system, 2 stars and a pulsar. And there's a few that have little bodies going around them. It looks a bit like planets. Not quite sure how that came to be, how that works. But there do seem to be one whose position just wobbles a tiny bit due to planets tugging them around. And because there's this fantastically accurate beat, you can see these little changes in position, which is wonderful. There's one in a triple system, and there's perhaps 100,000 in the galaxy, and there'll be similar in other galaxies. So for instance, the Andromeda galaxy will have its suite of pulsars as well. We think we know how they form, and we think we've seen in recent years one of the ways these things do form. We're looking here at a southern hemisphere object. It's a very small but nearby galaxy called the Large Magellanic Cloud, named after Magellan the explorer. It's a patch of nebulosity in the southern hemisphere. There's a small cloud as well. And it's a mini galaxy, a very mini galaxy. There's lots of pink stuff in these slides. That's hydrogen gas. The red things that you see in many astronomical photographs say hydrogen. And the main Magellanic Cloud is up to the left, but down to the right, and in particular in the left-hand photograph, there's one star that has an arrow pointing at it. Let me be absolutely clear, the arrow was added after the photograph was taken. The universe does not provide us with arrows telling us what to watch. But if you were watching that corner of the universe, you'd find that that particular star had exploded. It's a massive star, it's near the end of its life, and the way massive stars end their lives is with a massive explosion. And in the massive explosion, the core of the old star gets kicked against and shrunk down and becomes one of these very dense neutron stars or pulsars. So pulsars are formed in these massive explosions from the core of the star that exploded by the explosion kicking against the core. Call it a supernova. Nova means new, new star. It's an extra bright new star. Oh, clicker's working again. Right. This is in our galaxy. It's known as the Crab Nebula. Very, very interesting object. Star that exploded in 1054 AD. Big star, reached the end of its life, did one of these supernova explosions, observed particularly by the ancient Chinese and documented by them. So we know exactly when it went up, 1054 AD. In the middle of it, there is a pulsar. It's the core of the star that exploded. All that other stuff that you see shining used to be part of the original star, but in the explosion got spread out to make this nebula. And astronomers were puzzled by this nebula for a long, long time. We knew that it exploded in 1054 AD. That's very well documented. Why is it still shining so brightly now, 1,000 or so years later? It should have dimmed. We now know that right in the middle there is a pulsar wheeling around with its beam, keeping the gas glowing, keeping the thing shining, keeping it brighter than it ought to be all these years since it exploded in 1054 AD. And that thing that's keeping it bright is one of these pulsars. The pulsars are created when a particularly massive star reaches the end of its life, the star explodes. But it doesn't explode, so to speak, at the center. It explodes in a ring or a sphere about 10 miles out from the center. And the material inside that ring or sphere gets kicked against and gets collapsed to make one of these neutron stars. And the rest of the stuff goes out and forms all this wonderful glowing debris. Just to finish off, one of the lovely effects of having discovered pulsars is every so often somebody comes up to me and says, you know, I nearly discovered pulsars, and tells me the story. So this is one or two of these stories. It's 1957, we're in the USA at McDonald Observatory. McDonald specified the observatory is open to the public one night per month. It's that night. The telescope is focused on the Crab Nebula, which we now know has a pulsar in the middle of it, keeping it shining. They didn't know it then. The story is told by Elliot Moore, who was a student working there for the summer. And he's helping with this open night, and a young woman steps up to the telescope, and she says, that star's flashing. And the night assistant starts to explain about turbulence in the Earth's atmosphere, blah, blah, blah. She stops him. She says, no, this is 1957. She says, I am an airplane pilot. My job is to fly aircraft from the manufacturer to the customer. I fly at night. There's not a lot to do in the cockpit at night. I look at the stars. I know about stars that are variable. That star's flashing. Now that star does flash at a rate of about 30 times per second, which is pretty fast, and not everybody can see flashes at 30 times a second. Young women tend to be best at that. So we strongly believe that she saw the Crab pulsar, but the night assistant was having nothing of, being told what to do by this young woman. So he passes on. Australian radio astronomers got a very excited letter in June 2007 from an American called Charles Schisler. He had been in the military, he had been posted to Alaska. He was working on the US's early warning system, looking for missiles coming in from Russia. When it was quiet, he was allowed to play around with the radar equipment. And he's playing around with the radar equipment, and he's picked up some objects that are flashing, which aren't incoming missiles. They're genuinely stars. He'd done an astronomy course at college, and somebody had taught him about the coordinate system that astronomers use. And he did his very best to get the right coordinates of these flashing stars. Illegally, he took away with him at the end of his service that bit of paper that had the coordinates of those flashing sources. He's just discovered the online pulsar catalogue that the Australians keep, and several of his sources are in them. And full of excitement, he contacts the Australian pulsar astronomers. They checked him out. Sounds genuine, sounds really good. He came to a number of our conferences. So that's, where's the pointer gone? Not working. Charles Schisler is at the far end of the table. I'm next to him. And then some Australians that you might recognize. So we think he had actually discovered pulsars. But of course he wasn't allowed to publish, and he probably wouldn't know where to publish.
We're very close to done.
Yep, on the last slide, I think. Sue Simpkin is a professional astronomer. She was due to take some observations using a telescope. She's asked by Low Vulture, a Dutchman, to take a spectrum of Minkowski star, which is the thing in the middle of the Crab Nebula. Sue said the spectrum was dull, but she thought she observed it fluctuating. Low Vulture wouldn't believe her, but when the pulsar was discovered, he said it must have been. I'll skip that one. So I had my own telescope, my own receiver. I understood its behavior. But I'm a graduate student, so I've got time to follow things up. And remember, I'm not bright enough. Cambridge made a mistake admitting me. They're going to throw me out. I'm working my very hardest until they throw me out. And I stumble over this funny signal in my data. Interestingly, in Britain these days, you have to declare the objectives of your research program when you get funding. This was not one of the objectives of our research program. Would we have been penalized for discovering pulsars? If we had computerized the search, we'd never have programmed to look for something so unexpected. And I will skip Franco Pacini and end with a group photograph of some of the Oxford pulsar astronomers. Thank you for your interest. Thank you for your attention.
Okay, thank you for that amazing talk and for sharing all of those stories. Now we do have a little bit of time for questions. So we've got a couple of people here with microphones. If you have a question, can you put your hand up and wait till the microphone gets to you so that everyone else can hear? There's one over there to start.
How quickly was the telescope that you set up made redundant, and was there anything else found on it? Well,
Yeah.
considering
yes.
the speed of technological
Yes. Yeah.
development
Yeah.
in the 20s.
The grad student who succeeded me in using the telescope found one or two more pulsars, but it probably stopped being useful fairly soon after that. It just sat there in the field until the price of copper went up. And then one dark night, somebody came in with some wire cutters and took away all the copper wire. And that was that.
Up in the middle, back.
Thank you for the talk, Dame Jocelyn. I'm Augustia from Macquarie Uni. I had a question about chasing wild geese and how long before you start doubting if what you found is real,
Yeah.
and your journey through that.
Yeah. If it had been confined to just one of these objects, I think it would have been seriously in doubt. In fact, I found the first 4. So it was quite a little industry of itself. And once you've got more than one in a different part of the sky, perhaps beating at a slightly different rate, but clearly the same kind of object, it begins to feel a lot better. When you've got 3, it's even better. Then the 4th one comes in and it's beating about 4 times faster than the others. And you begin to think, oh, this is going to be an interesting field. Yeah.
Yes, I'm Jocelyn. Do you find yourself lucky because the first few pulsars you discover have a relatively slow spinning rate or scintillation rate? Mm-hmm. Would it make it much more difficult for you to discover them if they have a much higher spinning rate?
Yes, it would be. But they do age, and as they age, they get slower. So you're always going to have some slower ones for telescopes like this to pick up.
What's the typical spinning rate?
Well, the fastest one goes about 30 times a second, and the slowest is about once every 4 or 5 seconds. And then they sort of, you know.
We're finding even slower ones now. That's, yeah, hot off the press. This one of our microphone runners right here, Manisha Caleb, has been finding some very slow pulsars. Sorry, I'm just integrating you into the story. Okay, there was, yeah, exactly. Well done, Manisha. Look out for more results in nature. Over here, there's a question there.
Do you still feel like you have imposter syndrome?
No, I've managed to change the types of astronomy I do, the wavelengths I use several times, and I've learned to sort of brave it out. But it is something that women sometimes have to learn.
Yeah, definitely.
If you work in a male-dominated field, got to be a wee man, not a woman.
Thank you so much. This has been really amazing.
In the signal that you got from the over here, in the signal you got on the first one, you described that the pulses were very equally spaced, but there was a very large variation in the signal's amplitude.
Yes.
What was the explanation for that?
The radio wave is coming through space where there are charged particles. And it's the charged particles that slow the speed of the radio wave and slow different wavelengths at different amounts. So your pulse can end up sort of changing colour, to put it crudely, within the pulse.
Question down here.
Good evening, everyone. Good evening, Dame Jocelyn. What do you think is the best incentive to have more women in STEM?
Right, yes. This is an area that I've worked in a long, long time, and it's becoming politically, with a small p, more and more important. I think you've got Athena Swan in.
Yep.
Yep, I was one of the creators of that back in Britain. It's particularly difficult in a subject like physics. Biological sciences, there's much better gender balance. Chemistry is quite good. Physics and engineering have the smallest fractions of females. And the predictable result is that maybe the few females there are feel a bit isolated, lonely, ignored, think of lots of other negative words. It's getting better because there's greater awareness of the issues. And I think we're all on a journey, a learning curve at the moment on that. And I hope the learning goes on. I think there's been a lot of improvement since I was a grad student, but there's room for a bit more improvement yet so that women who are in a minority don't feel discriminated against. As always in this world, money amends behaviour. And in some places, in some countries, your funding will depend on the fraction of females and how well you retain them. That's a bit dire, but...
Okay, a couple more questions. There's one just there, yep, behind Laura. And a last question. Someone over here wants to put their hand up.
Thank you for the talk. You talked a lot about the kinds of experiments and the things in the spectra you were looking at to find the information you found about pulsars.
Yeah.
I was wondering if you could speak at all to how the information about what a pulsar actually is, this sort of neutron star, was found.
Right. Well, you can put constraints on the size of the object by how rapidly a signal changes. And it became clear quite quickly that they had to be really compact objects. In addition, you've got theoreticians working out what are the possible kinds of compact objects that you might find. Clearly couldn't be a black hole because it was emitting. And the black hole was almost a bit too small. White dwarfs are a bit bigger than pulsars. And then you say, oh, well, wasn't there that paper by a slightly mad theoretician about neutron stars? Maybe we should go look at that again. And that's what happened.
Final question for this evening.
I understand that the significance of the discovery may have taken some time to, from the moment that you finished your PhD. But what did you go on to do after having done something so significant? What was the next thing you worked on?
I got married. I got engaged to be married between discovering pulsars 2 and 3, if I can remember rightly. I'm no longer married, may not surprise you, but it resulted in a phase where you're trying to find good jobs for husband, who works in local government, and myself, who's a rather specialist astronomer. I became less specialist and more flexible about what I worked on. And every so often husband would say, it's time I changed job, because that's how he got promotion. There's a job going in, and he names a city. If we were to go to that city, is there anything astronomical anywhere near there for you? And if there was, I'd say yes, and if there wasn't, I'd say no. And if he got the job, I'd then be writing a begging letter to the nearest university and head of physics department saying, might you have a job? And at one point it had to be a part-time job because there was a kid. You know, all the usual kind of constraints of married life. It's not easy. Ultimately, the marriage broke up, surprise, surprise, and that actually got easier work-wise, although there's ups and downs.
Thank you.
I don't know if that's a good note to end on or not, but that's where we're going to end this evening, everyone. Thank you so much. It's amazing to be part of sharing the human side of the story of great scientific discoveries. So thank you to everyone that organised the event and our amazing young women scientists who have actually put this together and have been organising the events all week for Jocelyn. Thank you to Helen Stibbs for coming and supporting our yearly lecture. Thank you to Dame Jocelyn for sharing all of her experiences in such an interesting way. And thank you all for coming, and I hope you enjoy the rest of your evening. Thank you.
Thank you.